In this video, we're going to learn about the interval estimation of the population mean. Last time we have learned that we can estimate the population mean using the sample mean like this. Now a sensible question is, how accurate is this estimation? Indeed, we have already encountered a similar question when we learned about the error in measurements. For example, if a length is measured as 18 cm and the maximum error of this measurement is 0.5 cm, then we know that the actual length should be between 17.5 cm and 18.5 cm. In addition, we can use this plus or minus notation to indicate the range of possible values of the length. From this range of possible values, we can have an idea of how accurate this estimation is. Now for the case of the estimation of the population mean, unlike the case of measurement, it is not possible to obtain the maximum error of this estimation. As theoretically speaking, this error can be infinitely large depending on the probability distribution. However, in statistics, there is still a way to obtain a reasonable range of possible values of the unknown population mean. Let's consider the situation in this way. Suppose alpha is the probability that the range x bar plus or minus e does not include the unknown population mean mu. That means alpha is the probability that x bar plus or minus e is a wrong estimate for mu. And so we want this probability to be very small. Now we would like to see how the error e and the probability alpha are related. To simplify this situation, we can further assume that the population is normally distributed, so that the random sample mean x bar follows a normal distribution. Here we know that the probability that mu lies in the range from x bar minus e to x bar plus e is 1 minus alpha. Next, we try to manipulate this inequality expression so that we can obtain the standard normal variable z. To do so, first of all, we can multiply minus 1 to all the expressions and then flip the inequality sign. Then we can add x bar to all the expressions. And finally, we divide all the expressions by the standard deviation of x bar, which is sigma over square root of n. In this way, we can obtain the standard normal variable z like this. From the standard normal curve and the standard normal table, we can obtain the value of e over sigma over the square root of n. And this z value is known as the critical value of z corresponding to this situation. Therefore, we can get that e is equal to z times sigma over the square root of n. And this value of e is dependent on the value of this probability alpha. If alpha is smaller, then the value of e will be larger. Using this value of e, we can obtain a range of possible values of mu by x bar plus or minus e. In statistics, this range is called a confidence interval. And we can use this bracket notation to represent a confidence interval. Let's consider some concrete numbers for alpha. For example, if alpha is equal to 0.1, then the corresponding critical value of z is 1.645. And then the interval for mu would be this one. There is a probability of 0.9 that the unknown population mean actually lies in this range of values. So it is called a 90% confidence interval for the population mean. It means that we are 90% confident that this interval is correct. We can increase our confidence level by considering a smaller value of alpha. For alpha equals 0.05, we can obtain a 95% confidence interval by considering z is equal to 1.96. Similarly, we can obtain a 99% confidence interval by considering z is equal to 2.575. The higher the confidence level, the larger the value of e, and thus the larger the width of the interval. In general, there can be 4 cases as shown here. The population can be normal or not normal, and the population variance can be known or unknown. When the population is normal and the population variance is known, then the sample mean x bar will exactly follow a normal distribution with a known variance. And so we can obtain the required confidence interval in an exact way like this. If the population variance is unknown, Then we need to use the sample standard deviation S to estimate the population standard deviation sigma. And so we can obtain an approximate confidence interval like this. When the population is not normal and the sample size is large enough. By the central limit theorem, the sample mean x bar will approximately follow a normal distribution. And so we can still obtain an approximate confidence interval in this way. On the other hand, we can easily obtain the width of a confidence interval by considering 2 times z times sigma over the square root of n, or 2 times z times s over the square root of n if sigma is unknown. Now let's come back to our original question. How accurate is this statistical estimation? From the given information, we can try to obtain an approximate 95% confidence interval. For the 95% confidence level, the corresponding critical value of z is 1.96. So an approximate 95% confidence interval is equal to this, which is from 59.06 to 64.94. If we want a higher level of confidence, let's say 99%, then by considering the critical value of z to be 2.575, we can get that the 99% confidence interval is from 58.1375 to 65.8625. Compared to a point estimation by the sample mean, such interval estimations can give us a clearer idea of how accurate our estimation is. After this, let's take a look at 2 more examples and see how we can apply the concept of confidence intervals. In example 1, it is given that a confidence interval for the population mean is 7.7 to 10.2. If we further know that the sample size is 16 and the population standard deviation is known to be 5, then we need to obtain the confidence level of this confidence interval. To do so, we can firstly find the critical value of z by considering the interval width like this. After knowing that z is equal to 1, we can conclude that the confidence level k% is equal to the probability that z is between -1 and 1. Hence, we can get that k is equal to 68, correct to the nearest integer. Finally, in example 2, we are given a normal population with a known standard deviation. If we need the width of a 98.2% confidence interval to be at most 3, we are asked to find the minimum sample size required. This is a very practical question, because this can help us to determine the sample size needed when conducting a statistical research. To answer this question, first of all, we can obtain the critical value of z by considering that this probability is equal to the confidence level 0.982. Therefore, we can know that z is equal to 2.365. Then, by considering the width of a confidence interval in terms of the sample size n, we can get that n is greater than or equal to 67.2181 something. Thus, we know that the least sample size required should be 68. This is how we can understand and apply the concept of confidence intervals for the population mean.